Hello everyone and welcome to yet another episode of Darko's Game Dev Cookbook. Yeah, this is the only line I scripted really. Everything else I want to do without any script. I want to just go in and do some drawing, do some programming, and I hope you'll learn something and I hope you'll have fun. This video is going to be dealing with ray marching, a technique I explained in my recent theoretical video. You can find it in the channel. I'm gonna link it somewhere above so you can actually watch it. It's only a few minutes long. I definitely recommend you check it out before we start. You start programming with me here. It's really useful to know it. I will be explaining the theoretical part here as well, so whoever stumbles upon this video can also learn directly with this video without watching me in full resolution. First thing before we start, so we're gonna do, as I said, ray marching, and we're gonna be rendering a sphere. First thing, for those of you who are new to programming, new to graphics, new to game programming, game dev in general, just a kind of a note. Don't be afraid to make any sort of mistakes. Just if you don't know what you're doing, just keep going, keep learning. I've had a lot of you reach out and ask for advice. I know for sure that if you're trying to start with programming and you never programmed before, it can be quite challenging, but just keep on going. You need time and it will kind of fall into place. For those of you who are a bit more experienced, but also kind of, they're still growing a lot and stuff like that. My advice that I really want to give you at this point is also keep on going. But one of the most important things that I notice people can't or don't really handle well is never be afraid to say, I have no idea what I'm doing here, or I have no idea what this is. Never be afraid to say, I don't know. Just keep learning, keep going, and it's normal not to know anything, something, right? That's just a small piece of advice I really wanted to leave. I know some of you are finishing their universities and doing their master thesis. Just keep on going. It's going to be great. Don't worry. You just need time, and if you have the power of will, it will fall into place. Trust me. Other than that, let's kind of start digging into this subject. I prepared my little drawing tablet as well, so we can draw things as well. Hopefully you're gonna understand what I'm doing, and if you don't understand something, you wanna talk to me and ask me about things. I'm over on Twitter. I'm quite active. I'm a chatbot at this point, so feel free to drop a comment there. We can chit chat about these kinds of things. I'm always interested in seeing people learn, pretty much. So let's get into it. As I said just a second ago, we're gonna be doing a sphere. It's an evolution of ray tracing that we did a year ago, and your head is gonna hurt how easy it's gonna be to actually render a sphere using this technique. It's just mind-boggling how easy it is, especially compared to ray tracing and all of the math you gotta do. The trick with ray marching is that if you have this is your eye, right? You have the canvas, which is your screen, and you have an object, and we're gonna draw a few objects, not only one, but a few of them, just for the sake of explanation, although we're going to render only this guy over here. So what happens with ray tracing, as we did before, you shoot a bunch of rays through the canvas, in this case as many as there are pixels, kind of, right? So you shoot them, and then you inspect, did the ray hit something? Yes, it did. Color the pixel. Did it hit? Oh yeah, color the pixel, and so on. You do the same with ray marching, but you do it in a slightly different fashion. So if you say that you have this ray going straight here, this is your point P. With ray marching, you're not going to shoot this ray to infinity, like straight to infinity, and just do the ray sphere intersection formula, and then you're done, right? Instead of that, you're going to do it in iterative fashion. So you're going to be in this point, and you're going to say, hey, which sphere is the closest to me, or which object? Like, this one, cool, that's the distance to this sphere. The distance will be determined using so-called, as I said in the theoretical part, SDF functions, signed distance functions, right? So you're gonna take that distance to the closest one and just apply it to your current ray. And here you're gonna do the same, like this. Oh my god. like this. You're gonna do the same, calculate that distance here, and you'll keep on repeating that process, hitting or inspecting the closest one until you basically reach the sphere. So let's just kind of keep rolling. So let's say that this is the next distance because it hit the sphere again. And here you're gonna probably hit the sphere first. So you're gonna move that distance over here. So this point over here might be directly on the sphere. It can be close to it and such. Here you define some sort of a minimal distance. So in code we'll define a minimal distance, and then if you're below that minimal distance, that we're gonna say, yeah, we hit something, right? Cool. The other scenario is that your array goes here and it goes to infinity and beyond. There you're gonna have some sort of a threshold that says, well, I kind of went to this point, so my total distance is quite high and it's higher than a certain max, so we're gonna clip it. We're not gonna do anything. The catch with ray marching, like you have this ray marching loop that is gonna keep bouncing until you hit something. After the loop is done, the thing you get is this distance over here. That's the ray marching distance, right? And you'll see in just a moment how that works and why each of these bounces is also important and such. But this is the distance you get from ray marching. Of course, provided that you have SDF functions defined for any object you might want to intersect with, that is gonna return. So SDF, basically what it does, it's a function that returns a distance from a point in space, in this case any of these, right, to the surface of the object described by the SDF function. So this circle needs to have, this sphere needs to have some sort of an SDF defined that will say, well, from this point to this circle center, this is how you need to travel. This is the distance. So without further ado, I think the best idea would be to just dive straight into it. We're gonna do the classic shader toy stuff. Move our whole coordinate system by 0.5, so we go from minus 0.5 to 0.5 instead of 0 to 1. I also can kill this comment because it's not really valid anymore. And another thing, if you're not familiar with shader toy, that's fine. Just bear with me. We need to fix the aspect ratio. So actually your x and y, the distances of x and y are always the same, or the number of pixels of 0.6x is the same as the number of pixels of 0.6y. It's pretty much what it does. This color, we're gonna leave it colorful for now, so we have something to look at while we're doing stuff. And we're gonna write this ray marching loop. So we need to write this loop where we do the bouncing by certain distances, right? How do we do that? Well, we're gonna do it quite simply like this. We're gonna type float ray march. As I said, the operation of ray marching returns the distance from your point to the object. So the whole distance, the whole line. I'm gonna type dist equals 0. I'm gonna return dist. And here we're gonna say for int, just the regular for loop, nothing fancy. You can define the maximum like this. You can define max distance as well. We're gonna keep max steps as an integer. This is gonna be float. And if you remember what I said over here, this point can be doesn't need to be straight on the surface. It can be a certain number away from the surface, right? Which means that you need to have some sort of a number where you say, well, this is fine, right? This is intersection. So you're gonna have maybe min distance, something small. We can tweak it later depending on what we get. So you say here max steps I++ like this. And now you need to do some logic, right? You need to iterate. You need to move from a point, from this point, you need to keep moving. So you need to calculate the distance and move, right? So for the first iteration, we're gonna say that the vec3 iteration point, iteration position equals, yeah, okay. Ray march needs to take the starting conditions, the starting arguments, which is the array origin, and then also it also needs the array direction. We're gonna figure those out first, actually. So as with ray tracing or any sort of 3D projection thingy, you need to have the origin or the camera, right? And we can place the camera in the center, but also kind of one step back from the scene. So we're just taking a step back and looking at the origin of the coordinate system from one step back by Z. The direction, I mean, if you did the ray tracing tutorial, you know that what the trick we did with this was that if you imagine the screen as a three-dimensional and you're shooting rays through it, if you shoot a ray through this one, the dimension of this thing is actually, if you know, now you know that the canvas goes from minus 0.5 to 0.5, same goes with Y. That means that the position of this one will be pretty much this X and Y. X and Y, this is the point. So we gotta do the same thing for the direction of our, this is the direction not from the camera to whatever it's looking, but it's a direction from the camera to the specific point on the canvas. So it needs to have UVX, UVY, and also it needs to have some sort of, if you look into this distance from the eye to the canvas, it really, like, you need to make it so, I mean, you can make it whatever you want really, but if you move the canvas towards your eye, your field of view broadens and then you get this distorted image, but you have a super wide field of view. For those of you who are into gaming, you know that wide field of view can be beneficial in some scenarios, also makes you feel like you're actually going super fast. If you move the canvas here, your beams are, the spectrum of beams is much narrower, so your field of view is super narrow. The things look more straight, you know, and it's a narrower field of view. So we can do something like focal distance equals 0.4. Put it to whatever you want really. We can actually move the camera a bit further away, as you can put the focal distance to 0.6, and then we do focal. So now we place the canvas 0.6 by Z in front of the camera, which should be quite okay. We'll see just a moment how it's gonna look like. Cool. Of course, this can't be an integer in this case, and here we're gonna write our stuff. The iteration position is gonna be R0 plus RD times this direction times the a single times distance. Yeah, it's the current iteration position. Looking at the photo, the picture over here, the iteration distance will be the iteration position will be this point, this point, this point, this point, and then we're gonna need to calculate it each time we go through this pretty much. So we say iteration position equals the origin plus direction times distance. Cool. Then you have the float iteration distance, which is actually, let me think, yeah, get distance. We're gonna need to create this function, and we're gonna pass it the position like this, and then distance becomes plus equals iteration distance. Why? Because as I said before, in ray marching, you gotta return the total distance from basically from the canvas to the thing you just hit, right? Not just the iteration distance. So distance would be from this point to this point, that's the distance, and iteration distance would be each of these. You gotta keep on accumulating them each time to actually get the real thing. Here you're gonna say, well, if distance kind of went above my max distance, then just break. Also, if you want to break or close the loop earlier, you can also do it by checking if the distance is below minimum distance. Did I type mix? Nice. Mix and max. Anyway. Mean this, then also break, because obviously you hit something, right? You hit the condition to hit something, so you're good. You can go. For now, we can just leave this be. I also have this number as not really something that works, and we need to write this get distance function. So I'm going to do float get dist. We actually need to get a get the distance based on a position. So I'm going to type vector 3p. What you're going to do in your scenario, here you're going to set up your scene. Which I won't do now, we're just going to render a sphere. So this get distance will actually in this case be quite useless, and it will actually return the SDF of the sphere because we only want to render the sphere and nothing else. So we do this. And here we just do SDF sphere P, I guess. Also, we want to have the option to kind of extend this thing, so we want to render a sphere with different positions and radiuses. But before we do that, we need to explain how we get the SDF of the sphere, which will be actually quite, it will be quite easy. So if you go back to this drawing board, how do you know? So SDF basically is a function that takes a point in space, any point in space really, and tries to it gets you the value or the distance from that point to the object, to the surface of the object described by this SDF function, right? So in our case, it's a sphere that has a center, it has some sort of a radius, and the distance is this thing over here. That's the distance you need to calculate, you get with the SDF. So SDF of the sphere gives you this distance over here. Simple as that. So how do you create this SDF? How do you know what this SDF is going to look like? Well, you kind of see the answer already. So you have this point, which is a vector, or a point in space, and C, which is a point. So you need to get the distance between these 2 points, right? So you do something like this. Distance between P and C, cool, which is pretty much this thing, the whole thing. But that doesn't give you the distance to the surface of the object, which should be this point, right? Well, how do you calculate that? Well, obviously, since it's a regular sphere, you just do minus r, and this is basically the SDF of the sphere. It's basically distance PC minus r. Simple as that. Of course, if you take any point in space, you should have the same scenario, right? You should always have the same, reach the same conclusion, that the distance is this thing and this thing and this thing, right? Cool. So that's the simple explanation of what the SDF of the sphere is. And we just kind of write it in code, really. We just do this. GLSL has built-in distance function, so you take one point and then take the other one and get the distance. For a sphere is defined obviously with a center and a radius. So we're gonna do PC minus r. And this one will now actually define the sphere, which is gonna be, we're gonna place it in the center of the coordinate system, and we're gonna say that the radius is 0.4. Does not return a value, of course. Cool. So this means that we can actually here. Okay, this actually returns something. So right now we have no idea what's happening, right? We have no idea if we're hitting the sphere, and we need to check that. So here we're gonna say that float distance equals get distance, and we need to pass ray mark, and we need to pass it the arrow RD, and then we say if distance is less than maximum distance, so that means that you actually hit something, you didn't go to infinity. That means you hit something, which means that the color will be, and we're gonna move this time varying color like this. Cool. And then of course this time varying color is not really helping us right now, so we're gonna keep that black just for simplicity. Cool. And now if you watch the ray tracing tutorial where we actually made the sphere, your mind will probably hurt. It will hurt because you did all of that math, and you could have done the same thing, literally the same thing, using one line, kind of. Ignoring the fact that you need to write this small for loop. Because the catch is in the detail, right? So with this thing, with this formula, you can basically render a sphere in 3D space with no issues. Of course, now it looks like a circle, but we're going to add some things that will actually display it as a real 3D sphere. What I want to do as well, I maybe make it a bit bigger. It's a bit too small, and maybe it's a bit too red at this point. So gonna make it a bit greenish like this. I don't know. So this is our sphere, right? Cool. And now we need to display it in 3D space. What is the thing that gives an object this feeling that it's a 3D when you're looking, of course, when you're looking at it in on your 2D screen? Obviously, a lightning or any sort of shadows or lightning. That's what gives out this 3D-ness of a thing, and we need to introduce lighting to this scene. But if you watched one of my previous tutorials, you'll quickly realize that there's one thing missing from this whole calculation. So we know that we hit something, and that's great. But if you want to calculate the lightning, one of the basic models, like the most basic model there is the model in which you just perform a simple dot product between the lighted direction and the normal of the sphere. So we need to get this normal. So if you draw the sphere over here, you quickly realize that, well, okay, if you hit this point over here, the normal will be this, right? And that's correct, but I don't want to do that. I want to do something that will be generic to the point where you can define any sort of SDF for any sort of object, and you still get the correct normal. And for that, we're gonna need to do some logic. We're gonna make a trick for it. So how do you get the normal of an object that you have no idea, you have no other information about that object besides the position? In this case, that's gonna be just the closest thing to the object possible. So in this case, this is our RO, or the starting point RO, and let's say we say that we proclaimed that we hit the sphere. We need a function that's gonna be called something like getNormal. That's gonna take a vector 3. That's gonna be this one, and based on that, return a normal. I mean, how crazy is that? You feel that you don't have a lot of context, right? It feels like you're missing something and there's no way you can do it. Well, here's the catch. With remarching and SDF, you can actually do that. You can do it because you rely only on distances. Throughout the whole thing, you just rely distance. You can always call a function that actually gets you the distance. So with what we're gonna do right now, we're gonna calculate the normal or get the normal based on we're going to dislocate the point where we hit the sphere, kind of, and then based on those dislocations, we're going to formulate a new vector that's going to be our normal. And how is this magic happening? Let's see here. Let's draw this simple coordinate system like this, and this is your y, this is x, and let's say that there's a surface, or let's say this is your sphere, but we are so zoomed in, so zoomed in, that your sphere, like we're just seeing a small chunk, like a nanometer of the sphere surface. So the radius is somewhere below, really far. So we see a chunk of this sphere's surface. And let's say we hit that surface here. So this is your point. This is where you hit it. So this is the point that we have for this get normal function, right? Get normal. So this is the position, vector 3. How do we get the normal only based on this? So the thing we do, we're gonna dislocate the coordinates. In this case, we actually we can act like there's only 2 coordinates in our case, not there's no z, but we're gonna apply it to the z coordinate in the same way we're gonna do here. You take a certain distance, certain epsilon distance, we call it epsilon, and we move both coordinates in the same way. So let's say I don't know, maybe let's do this. Let's subtract this epsilon. So we subtract from the y. We subtract, let's subtract 2. So 1, 2, somewhere over here. And this is your y copy basically. Then we subtract the x as well by 2. Here it's almost like a bit above 1. So we go this, right? Somewhere over here, you have your x copy. Perfect. And now what? Like, what is the context? What do we get from this? Well, we dislocated x and y. We need to calculate now. We calculate the distance from this point to the surface, like the shortest distance, of course. And we do the same for x and y. So we get this and we get this. So those are the two distances that we get. Okay, cool. Still, what do you do with this? Well, here's the thing. Like with SDF, it always returns a number. So if you have a point over here, it will return the distance. If you have a point over here, it will still return the distance, right? But the catch with this is that the sign of the distance can also be negative, can be positive. It only depends if you're inside or outside of the body. So this is inside of the sphere, this is outside of the sphere. So these 2 points obviously are on the opposite side of the sphere. So this one will be, I presume, it depends how you set the SDF up, but this should be positive, this should be negative. And what you do here, we're gonna draw a separate coordinate system. What you do here, this is a bit more than 1, right? And we said this should be on the negative side, or actually it might be on the positive side if we check the thing we did before. So the formula was the distance between P and C, right? Minus radius, the C. Yeah, exactly. So the distance between this point and this in the center is smaller than the radius, right? Yeah, and if you take this y copy minus, or the distance from y copy to the center, it's smaller than the radius, which means that this will go to the negative. So it will be negative. This will have a negative value. The x, on the other hand, component will have a positive value, because obviously from this point to the center, somewhere far from on the bottom right, this distance will be larger than the radius, so it will be positive. So you do the same thing on your small coordinate system. You say, well, y is 1.2, I don't know, something like that, but it's negative. So we have 1.2. So this is y, 1.2 minus 1.2. X is minus, look at this, this is funny, but it's not funny, but it's, yeah, shouldn't be like this. But anyway, let's say it's 1.6, and it's on positive. Cool. 1, 2, 1.6, 1.6. Cool. So you have this point. So if you have these two, you get something. And that something should be the normal, right? But I mean, when you're doing these sorts of things, you realize, oh wait, but shouldn't be the normal, because okay, this is my sphere, it's my body. Obviously, this normal is pointing inside. Cool. Well, what we did here, we kind of took this point and we did minus something instead of going plus something. So it kind of just inverts the things. So what you can do in this scenario, you're gonna say, well, okay, the normal is definitely correct angle, which is great. So I'm gonna invert the whole logic. So if you go back to your drawing board here, you say, oh, okay, so I took this one and then I did x minus epsilon and y minus epsilon. Instead of doing that, we're just gonna do this, which will make the y go here, it will make the x go here, and all of this will kind of look like this instead. And you get your normal. It's pretty normal. I mean, you could foresee these things quite easily, but if you're just kind of trying to make it work and see if it works, you're gonna end up in this. But you can realize easily, oh, okay, this normal is definitely going the opposite way. It's going towards the center of the sphere instead. So we're gonna do these two operations to get the component of our vector. Okay, so now when we kind of assembled this vector, how do we get this vector? So we said that we have to calculate this distance of dislocated x and y. We need to do that in code as well. So we're gonna say float vec3 get normal like this, and here we're gonna say if we think about what we did, we need to have some sort of an epsilon. I'm gonna name it t 0.01, and here we're gonna do something called swizzling here. We're gonna take this vector 2 and make this 0, make this 0.01, and what we're gonna do, let's get normal. We said okay, we take a point, right? Take a point. We're gonna take that same point, but instead of we're gonna take that same point, but then we're gonna use that point to get the distance to the closest object to that point. We should kind of, when you're trying to get the normal or something, obviously that point is probably close to that surface. So you have this, let's think about it, vec3 normal equals, it's gonna be get distance p, which is gonna be the distance from this point to the surface of the sphere, right? But we also need to offset the x component first. So we do e of x, y. So you only affect the x because this x is 0.01, right? So that's your x component of your vector. This is of course going to be vector 3. Then the y component is going to be the same thing like this one, but you're going to move the y component instead. So you do this, and you do this as well. Cool. And then this, of course, the normal you get is not really normalized because it really depends where the points is and so on. So you're gonna return. No, this is gonna be. Yeah, maybe we should just. Can't call it really a normal if it's not really a normal. So we can do this and then return normal, or just return this. And this will give us some interesting results if we do, for example, if we do this. So the point where you hit the sphere is actually this one. You take the RO plus the direction times the distance, and that's where you hit the sphere. And then you say, well, give me the color of my normal. Yeah, get normal be hit. And then you get something like this. So it's a sphere that now shows, uses x, y, and z components of the normal vector and kind of translates them to RGB channels to display them in a color. So R would be X, G would be Y, and B would be Z, pretty much. So if you think about this, let's see. Okay, it seems that on the left side we have too much redness, if you ask me, because the red component is now mapped to X, meaning that we have X that is negative on the left side. That doesn't sound really great. So we should be seeing the right component more on the obviously on the right side. Same goes from the bottom. So you can see that the green component is not really playing well at the moment, because you want the bottom of the thing to be you want the bottom to be less green. So what we can do, I think we just inverted the normal, and as I said in my explanation, of course we inverted it, so I just wrote it as negatives here. This gives you something that should be okay. Let me think about it. It goes the Z goes to -1, it goes towards you. Yeah, exactly. So there's no blueness on this side. This looks like a correct, like the correct normal. Cool. So I did the same thing as I did when I started calculating the components in the image just a second ago, where I kind of subtracted instead of added them together. But these kinds of things, like you will often you will end up in a situation when your normals are inverted, but it's just a matter of oh yeah, you can see it. I mean, you see that when something is inverted, that you should probably just change the logic a bit. Sometimes you just add the minus sign if in case it makes sense to do so in those types of scenarios. So yeah, dislocated x, y, z, got the normal, and now when we get have the normal, this is your sphere kind of ready to be lit because it has some normal. So you have that context. So we're gonna do float get light at 3 p. We're gonna have something like yeah, we can have directional light. Maybe that's the easiest thing to do, or yeah, we can have directional light like 3 light direction, and we can light the thinking if we should, no, let's make it point light. So we're gonna have light position 0, 2 or 3, maybe even higher, and 0, and then we're gonna have our point where you hit the sphere, obviously. So we can calculate the direction of this point light by calculating the vector from the point or from the light position to the point where it hits the sphere. So we have this thing. Okay, and then we have the get normal, pass it the point, and you do dot product between those two. That's like the easiest, the simplest form of lighting you can get. Perfect. So hopefully this works well. We're gonna see in just a moment. So we're gonna get the light. And of course the light now just returns, it's not the color, it just returns the intensity. So we can take the color and then multiply it with intensity. It looks inverted because obviously, I mean, dot product, if the normals are going against each other, it's a negative number. So this is one of the situations I said where the minus sign has sense, because the negative sign means the basically they're going towards each other, so it should be lit. And I also want to move the light a bit towards the camera, maybe even more, like this. Like this. And then I want to say that the sphere itself has some sort of a color. I don't know, let's do this. And then the color, we're gonna multiply it with intensity. Cool, and we also I want to have some, in all sincerity, I want to have some ambience to it as well. So I don't want it to be totally dark on the bottom. So what I want to do, I can actually clamp it or make it so that the minimum value is never really 0. So that's the thing, the simplest thing. So we're not using any lightning models right now. In other lightning models, we would actually have the ambient component as a separate component. Or we do max 0.2, and then we have yeah, of course we can't do this. Of course we can't do this because we're doing a maximum of a vector, which won't really work. But if we do this, oh yeah, I'm doing it in the wrong space, wrong place. Yeah, cool. Like this, and then we can maybe. Now is the time for you to kind of. I'm doing focal distancing. Or sorry, camera positioning. Brought it a bit closer, like this. And I also Yeah, this looks good. And then we can also do, just for the sake of just for you to see that the light is actually there, we can do sinus of I time. Okay, so we can maybe make it go double. Okay, and I would actually move it a bit back again. Cool. So you can definitely see that this is a real sphere, right? And you can see that it's three-dimensional, and now you also know that how to get the normal, you know how to calculate the SDF of a sphere, and so on. If you wanted to have multiple objects, then you would inside of this setup sphere, you would do you would have multiple results of SDF functions, and then you would choose the minimum, because obviously that will be the closest one to you. Or in this case, sorry, you wouldn't choose the minimum. You would kind of just invoke multiple of those functions, and then you would determine which one to return as the distance. You would get something there, right? But we can do that in one of the future tutorials. For this one, I just wanted to show you the basics of SDF. One more thing I want to do before we finish this video, I want to show you why SDF is so powerful, if in case you haven't realized it yet. So this sphere is just a regular sphere. If you wanted to do any sort of magic with it, combine spheres, you could actually do that quite easily. And we're going to do that in one of the future tutorials. I'm going to leave something for that as well. But the simplest thing you can do to see how easy it is to tweak things is that we can say that this radius of this sphere is actually not really static. So we can say that this texture over here serves as some sort of a height map to the sphere. Now, we're not going to do the Arcus Tangens thingy right now, and polar coordinates and stuff like that, because it's really not in the scope of this. What we're going to do a really fast hack just to kind of show you what this does. So here for radius, what we're going to do, we, instead of the radius itself, or not instead, we're going to add a certain height that we're going to read from the texture. So I'm going to say texture I channel 0, and I'm going to say I need to choose the pixel of the texture. Obviously, since this is a sphere, you need to have you need to use certain methods to kind of wrap this texture around the sphere to make it render correctly. But we can cheat here because we are looking at the sphere just directly and not going around it at the moment. So if you use the point, I think X and Y coordinates in this case, and we're gonna also move like this, texture. Okay, so we're having something. So we took the texture, we moved the X and Y coordinate. Oh, sorry, I think point. Yeah, okay, I don't think I need this really, but we can do this. This is way too much. Maybe we can do it like this. Okay, yeah, exactly. So I thought I maybe need to walk by 0.5, but I don't see. Yeah, the texture looks like we cheated the system just enough, so you don't see that the texture is actually wrapping in a really bad way behind the sphere. You don't want to see that, so we're just gonna keep that. Don't trust games; they do all sorts of crazy things with this. So what I wanted to demonstrate with this thing, and now it's, I mean, this thing is purple, obviously, and the catch is, what am I doing? Yeah, okay, we don't need this. The catch is, if you ever wanted to create a planet real fast, you never had the easier way of doing so. So right now you could argue that this is a moon, right? Of some kind. Not the best ever. It is pretty decent, I would say. And also, I mean, the things you can do are, I can't even start explaining, but look at this, for example. If you do have this and then you do this. Then you have a breathing planet. Obviously it doesn't look right because the sinus goes negative, but hear me out. If you do, let's say, +1, so you don't go to the negative side, you just have a breathing organism that looks like this. There we go. I mean, what did you do here? You had a point, you had the radius, and you had one formula and one for loop. And you have something that looks like a golf ball on having a really bad time. And of course, the parallax effects here are a given. They're just, you don't need to do any sort of layering and anything like that, like we did with the crystals. I mean, you have this here. It's directly built in the logic of SDF as you actually, each of these ridges, each of these holes, they are real in a sense. So the ray actually goes there and really intersects with the object. So right now you're intersecting with an object so irregular that you would have so much trouble building the same thing with ray tracing that it's impossible to comprehend. And with this, you do it with one line. That's the power. And in one of the future tutorials, I'm definitely we're gonna build something like a few spheres interacting and having these basic. We're gonna explain the basic operations you can do in SDF that show you how different objects react. But this is how. Yeah, I might actually leave it like this, or we might. Yeah, okay, we'll leave it like this just for fun. So I will save it like this. So the project you're going to open is going to look like this. But yeah, now you know how ray marching works. It's really not that hard once you step into it, once you think about it. I think maybe the trickiest part, and you saw in my example, just figuring out the normal, like you would get these inverted scenarios really often when you start thinking about it, you're going to mess something up and you go the different direction. But the most important thing is that you know exactly when you get something, you know why you got it, and then you can kind of roll back and see, yeah, it's the opposite, and then you do that pretty much. But yeah, that's pretty much everything I had for today. If you like this thingy we made here, the golf ball on steroids, please do hit that like button. It really means a lot. Also, if you're new around here and you're watching this content for the first time, please do hit that subscribe button. When I see things like that, it gives me the incentive to keep working on things like this, because I know that someone is actually learning from it, and yeah, it gives me the power to kind of carry on with these kinds of things. But yeah, until the next time, yeah, stay healthy, stay safe, and I'll see you with the next tutorial.